Hi, welcome to Unit 1, beginning with Chapter 12 in our 13th edition of Thomas Calculus. Please make sure that you get the right book. Let me say that this part right here is not on the cover of my book. This just happened to be the image that I use. So it should be, here, let me show you. Thomas Calculus, I don't know if it's fully in the screen, and down here it says multivariable. And it is serial number 0-321-88405-1. If you get any other serial number, it will be the wrong version of the book. Multiple books have the same cover, and they just alter the titles down here. So please make sure you have this one, and you'll be doing the right thing. So we're going to proceed with section 12.1 now, and just talk about three-dimensional coordinates and talk about how we draw them and represent them on a two-dimensional piece of paper or a two-dimensional screen. So take a look at this image. In it, we have the positive end of the x-axis, the positive end of the y-axis, and the positive end of the z-axis. And so we're only really representing one little section of three-dimensional space. And because a coordinate system like this, if you were to extend the axes out to see the negative ends, this would divide space into 8 regions. And so they're called octants, with an O, octant. And so we only really draw the first octant. And while we can try to learn to draw in other octants, typically speaking, we focus on the first octant and we don't really number the others. So we may be drawing into the negative halves of the various planes, but mostly we'll focus on the first octant. So here you can see point P is represented by the coordinate triple XYZ, and so that means that we started at the origin, 0, 0, 0. We went down X units to this point. We went over to this point, Y units, and then we went up Z units to arrive at the point XYZ. The other thing I want you to notice is the picture of the hand. The right-hand rule of thumb, which you may have heard about in physics class, orients this quadrant so that, and you have to picture this, if you wrap your hand around the z-axis and you go from y around to x, or from x around to y in that order, you can think of it as wrapping it from y to x, or starting at x and curling it around z toward y, that your thumb points up. Your thumb is the indicator of which direction is positive for z. So with the right-hand rule of thumb, up would be positive for z, which is nice because that makes sense. Okay, so, and by the way, I've never heard of anybody using a left-hand rule of thumb. So sad for all of us lefties out there in the world. All right, take a look here. It's a representation of the planes x equals 0, y equals 0, and z equals 0. So over here, I know they're all labeled. So if we've got x equals 0, that's the green plane here. Notice how it appears to be vertical. It's only green on the top half. It's kind of non-green on the bottom half. I don't understand their color choice there. But that is the plane that every point on that plane, x is 0. So the equation is actually a description of every point on the plane. Well, then we want to see y is 0, and that's the pinkish-reddish plane here. Every point on that plane, y is 0, and x and z take different values. And then in the blue plane, it's kind of like a tabletop, that is the z equals 0 plane, because it doesn't move above or below where z is 0. So those planes actually help you see the 8 different regions in space. All right. Then we put more detail in. So we've drawn planes in other locations, and we've also drawn where those 3 planes intersect. So we've got x equals 2, we've got z equals 5 in blue, and we've got the reddish plane y equals 3, and they cross in the point, unsurprisingly, 2, 3, 5. So you have to kind of picture down 2, over 3, and up 5 to get to this point right here. All right. Then we need to practice kind of anticipating what these equations and mostly inequalities look like geometrically. So pause the video right now and see if you can describe with words what each of these graphs represents. Okay, if you have Let me see if I can mark the video right there. Add a marker. Okay. So if you press play, have pressed play to continue, pardon me, we can now begin to talk about what some of these represent. So z is greater than or equal to 0. Everywhere that z is positive would be everywhere above the origin and above the xy plane. So it's half of space out there. So the half space consisting of the points on and above the xy plane. So the on part refers to the or equals to sign. So let's think about x equals -3. Well, we've seen planes. I want you to decide which direction x equals -3 goes. It goes through x equals -3, so it would be going up and down. So you kind of have to think about these. So this is the plane perpendicular to the x-axis. At x equals 3, it's parallel to the YZ plane and 3 units behind it. That's a very thorough description. So I'm going to let you read through the rest of these. These examples are, of course, from your book, and you do not have to read your book before coming before coming to the lectures. Listen to me before listening to the lectures on video, because we'll be using the book as a guide to our discussions, and you can refer back to it when you're looking at your notes and working on homework. So think about the rest of these answers, and I will not go through every single one of them on the video. If in live lesson time on synchronous lessons you want to ask about some of these, please feel free to bring it up. Okay, so we want to be able to tell, looking at equations, what points would satisfy both of these. So if we've got x squared plus y squared is 4, well, in 2 dimensions, since it doesn't have a z in it, that would be a circle with radius 2. And z is allowed to be whatever it wants to be. But then we put this additional constraint on it. Z would have to be 3. Well, I want you to imagine, before I move the box out of the way, what this might be. Okay, so we want to be able to picture it. We also want to be able to describe it. So pause now if you want to think about it. And when you hit play, you can take a look at the answer. Just don't peek ahead in your book when we do this. All right, so if you're returning, here's a great picture of this. You see we talked about the circle in the xy plane with a radius of 2, and then requiring z to be 3 means that we have to shift the blue circle up 3 units above the xy plane to be floating above here at where z equals 3. So if we didn't leave z equals 3 in there, if we just looked at this in only 2 dimensions, it's a circle. In 3 dimensions, it would be all of the circles vertically up and down forever with radius 2, which, when considered together, would be a big open-ended cylinder going to infinity up and down, wouldn't it? All right, so since this equation didn't specify what z had to be, z can take on all values. And then when we limit it to z equals 3, that's when we get a single circle. All right, so there are some very predictable things in 3 space where the algebra is concerned. And here's a nice long proof of the distance formula in 3 dimensions. I bet you're not surprised to see the actual formula down here looks a whole lot like the 2-dimensional one, especially up to this point. It's identical. And then we kind of throw in the z2 minus z1 quantity squared to make it 3-dimensional distance formula in space. So throw in is not a proof of anything, so I want you to peek through this proof. Notice how they use 2 versions of the Pythagorean theorem to come up with the distance formula for, and these lines represent length, the absolute value of the line segment from P1 to P2. So I want you to go through that carefully. Homework questions sometimes will ask you to use a proof to find something before it asks you to use the formula to find something. So please be reading through that. Okay, so now we want to try it on our own. What we've got here is, let's see, get my pen. So we've got d equals, got to remember the big old square root. That's the one thing some people forget is the square root sign, even though they know better. I kind of set it up in skeleton form, I call this. And so we're going to do x2 minus x1, -2 minus 2, and then 3 minus 1, and then z2 minus z1, 0 minus 5. So we're going to have the square root of -4 squared is 16, of 2 squared is 4, and of -5 squared is 25. So this is going to be the square root of 20, and 25 is the square root of 45. And I'm going to relieve you of the responsibility of simplifying every radical in sight, but if you're being responsible to your earlier math teachers, this is going to be 3 square roots of 5, and that is the distance between point P1 and point P2. All right, as always, if you would like to work a problem before you hear me explain it, just hit pause. Okay, so if the distance between 2 points, say P naught or P sub 0, I'm going to call it P naught, and P would be the radius of this sphere, we're going to call that length A, then if we square A, then that gets rid of the radical on the distance formula and gives us a very predictable formula for a sphere whose center is at the coordinate triple x naught, y naught, z naught. So that's a rather common sense consequence of the distance formula in 3 space. All right, so find the center and radius of the sphere. So now's your time to remember how to complete the square. It's probably been a really long time. So pause this if you don't care to see it and you want to see if you remembered on your own, and then join us again when we're done. Okay, I'm going to group these. Y squared, see there's no other y term, so we're good there. And then we'll do z squared minus 4z, and then we're going to move the 1 over to the other side of the equation to get it out of our way. So we're going to add in, and this should be a z. I crossed my z so they look different from 2's. That's a little close, so here we go. We've got to take this coordinate, cut it in half, and square it to get 9/4, which means we just added 9/4 to the left. And then we have to take -4, cut it in half, -2 squared, and add 4 to complete that square. Add it on the right. And that would give us x plus 3/2 squared, and y squared, and z minus 2 squared. And then we've got 3 would be 12/4, plus 9 is 21/4. And so our center would be -3/2, 0, 2, and our radius would be the square root of 21/2. Don't remember that this is the radius squared. So there's the length of our radius. Alrighty, so moving on. I think we've got one last slide. Now we want to be able to describe spheres in space based on an equation. So we see x squared plus y squared plus z squared. This is going to be a sphere centered at the origin. And the less than 4. So we got to interpret the inequalities here. So it never equals 4, so it doesn't actually include the boundary, the shell of the sphere. So A would be the interior of a sphere centered at the origin with a radius of 2. Okay, with that in mind, pause this and see if you can figure out the others. And I'll move the box off the answer key, off the answers when you get back. All right, so moving this up. Here we go. So I'll discuss one more. Let's look at D, and you can ask me questions about the others if you have it. So without this inequality at the end, this is just a sphere of radius 2 centered at the origin. And then if Z must be less than or equal to 0, that's everything on the bottom half of the sphere. And since it's equal to 0, it would be the points that lie on the XY plane. So it would have that rim. And it would include the points on the shell of the hemisphere on the bottom as well. So interior, boundary, and equal to 0. So make sure you kind of cover all 3 points on something like this. All right, that's your very first lesson, and we'll continue with 12.2 next time.